Okay, we'll get going here. My name is John McQuillan. I'm supposed to be the facilitator for this session. I work in the low gravity exploration technology branch at NASA Glenn Research Center. I've been involved with low gravity research, especially boiling and two-phase flows, for the last 33 plus years. My colleague, Tyler Hatch, he'll be taking the notes for this session in case I miss anything, which is highly likely. And we look forward to an active discussion. Let's see. All right. Just kind of as an overview, this breakout session lasts for about an hour. There is a subsequent breakout session. Depending upon what type of attendance we get at this one, and if there's a different crowd at the second one, we may or may not have the same topics discussed. Feel free to either stay with this session or move on to a different session. Please sign in using your full name so that we can see the name of the attendees. And I also ask that you mute your mic unless you're speaking. But to get my attention, please raise your hand. If you look at your Teams screen, up in the upper right, there's the ability to raise the hand. It will open up a little icon. Let me see. It'll open up a little icon like this, and you just click on that and bang. Your hand is raised, and then when you're done, click it off. Feel free to add questions to the chat, and we'll try to discuss those as well. Moving on, as Lisa had mentioned earlier today, let me see if this is working. We want your input, and this just isn't the science community. We also got a fair number of technologists involved, as well as other members of the space community involved. But we have three objectives, and I'm going to try to focus it primarily on the first two, and the third one may actually fall out of some of our discussions. But if we don't have a lot and we got some time, especially if we got time left over, we'll talk about those at the end. So moving forward. Where do we see the top physical science knowledge gaps and research topics that we must conduct either on the moon or in the near lunar orbit? And ideally, we'd like to get some idea of the priority, but the key here is to enable sustained lunar habitation and future Mars missions. Not necessarily to enhance, but to enable. In other words, if we don't do it, we don't go. And along those lines, in terms of the enabling or the order of priority, obviously we want to try to address the things that are most important up front. So do we have anyone want to take the lead on this? Yes, Bonnie.
Yeah, I think an area that I'm pursuing is partial gravity two-phase fluid physics, because I think it's pretty fundamental to understanding heat and mass transfer. And I'm just wondering, what are the plans for doing any situ work in 16G?
What I know, and again, I sit at the wrong end of the spectrum. I'm not necessarily a planner. Maybe if Jim's aware of anything, but one of the limitations that we're running into is with regards to these, what they call commercial landing or commercial landers program, is both thermal. We have, wherever they land those landers, we have a limited mass that we can carry, at least for the initial rounds. We're trying to pursue that. We have limited power and we have limited data bandwidth. And so unless it's a very small type of experiment, right, at least in the near term, there's very little. And I guess I kind of want to go back to what Morgan Abney said at earlier today. But she doesn't necessarily, some of the two-phase flow issues will kind of go away, or they're not as concerned. And the reason being that they believe that gravity will continue to play a role. You may have to size things a little bit differently, such as your separators, but there may be other issues such as stability.
Okay, if I might add, we've been doing some CFD modeling of gas and liquid in contact with various solid surfaces, because in the microgravity environments, surface energy dominates, and of course convection dominates here in 1G. And we've got some very interesting results at the low G levels. We validated the CFD at 1G, and we were invited to participate on the Nova-C lunar lander and had developed a 1.5U experiment to fly, but we couldn't come up with the $2 million. The university couldn't. So I think there, I've had 5 flights, and we're always surprised by the role of the materials that are in contact with the liquids and gases. And I think that's an area we still need to pursue.
Okay. Let's see. There's a question here, or a question here from Heather. This is a life support and thermal session. That's yes, Heather, that's correct. And then Gareth said, what is the knowledge of knowledge on cabin air quality beyond the immediate concerns of regolith dust and CO2? The development of a cabin aerosol science and micro or lunar gravity, especially with regards to unique indoor air chemistry that will be present. Jim, you've got a question?
Well, I was just going to weigh in on that question. We do have some aerosol and particulate monitor experiments we have on ISS that we then hope to combine and miniaturize to help characterize the aerosols and small particles on the moon and help us distinguish between crew generated versus lunar particles versus compounds that may form. And we do have sort of a debate in the life support community for measuring chemical compositions. We think we understand what evolves in a spacecraft on ISS fairly well, but should we be able to detect an unknown using a broad spectrum instrument, or should detection be targeted on compounds that are generally of concern? And so there are different instrumentation strategies, and so that's a active area of discussion, but we do have work in both areas.
And I believe there's also discussion about just in terms of the sampling, the sampling size, the sampling placement, things along those lines. And that leads into a separate issue in terms of noise, because they want to use fans to kind of homogenize, at a minimum, homogenize at least some of the air quality within the spacecraft, correct?
Correct. How many instruments do we need? Do we need one per module? Some debate as spacecraft get smaller, at least initially, can you get by with, just one? Or do you have some distributed array, maybe for major constituents like CO2 bubbles, but then for detailed trace gas, maybe there's a less number of instruments? Or how frequently do you run these things? Because everything takes a consumable. So some discussion, do you have instruments for sort of coarse monitoring of quality, like on water, we measure total organic carbon, and then periodically we'd like to be able to speciate all the chemicals and microbes in the water, but we wouldn't do that continuously real time. So it's a balance of information, and resources, and what would you do with that information?
Okay. TJ or TG.
Terry Gordon. Yeah, I'm on Heather's question and what was just mentioned. Yeah, once you have that information, what do you do with it? So I'm sort of curious I know it's physical sciences, but I'm primarily interested in human health. I was on a human risk panel, and that sort of dissolved. I was on the water and air exposure guidelines that NAS ran, and that was dissolved. I was chair of the Lunar Dust Committee. That was dissolved after about a year. So who is taking the information on the physical science of the exposures, thermal, particles, radiation, and doing something with that to protect the astronauts? Because as the exposure guideline committee, as they told us, the NASA personnel, this isn't a regular occupational exposure guideline committee. This is, you got to think 5 years in advance what there might be so the engineers can build it into the spacecraft. You only have one chance. So is that dialogue still going on to answer what Heather was talking about?
I do not know if the dialogue is still continuing. My group is more or less along in terms of physical sciences are more into the research end. Why is boiling different in microgravity? I do know that there are multiple aspects with regards to the exposure guidelines, and you are correct. Part of it, there's actually 2 or 3 aspects. One of them being you're designing a spacecraft that may fly anywhere from 4 to 10 to 15 years out. So you have to kind of be anticipatory in terms of that. I also know that in some cases, such as like the ISS or a lunar habitat, there may be, unless you have the ability to scrub either your water or your atmosphere sufficiently, there's a gradual buildup of those potential, and I don't want to use the word toxins, but toxins would be contaminants or things that would have a negative impact.
Could I just pipe in a second on my question?
Sure.
So one of the things that I know that there was some research done. I can't remember if it was on Space Shuttle or ISS, but they were seeing a physiological response in plants that they had an issue with it. They weren't really sure exactly what was causing it at some point in time. And so the data of like the plant, how the plants grew and what have you was fairly skewed, and it was determined down the road that the problem was buildup of ethylene gas that was causing the plants, basically to, if ethylene gas is what makes fruit ripen, for example, but it's a hormone and it affects, physiology. But I'm not an expert in this area, but I am an engineer that works on designing bioregenerative life support systems. And so, and work with like Dr. Wheeler and Dr. Massa with veggie and some of the other experiments. But I think that those types of volatiles are going to need to be scrubbed. And so whenever I'm currently a PhD candidate at CU, so when I'm designing these kinds of things, we always sort of do this hand wavy thing that says, well, ECLS will take care of, removing these kinds of volatiles from the atmosphere. But I don't think that they've been fully characterized. And then if you go into things like aquaponics, where you may have fish and nitrification bacteria and things like that, I'm assuming that those, in doing worm composting, that all of those are going to be producing additional volatiles. And so I think if those are really viable options, we at some point that all has to be characterized.
I know ISS has what they call the trace contaminant control system, and it actually has 2 parts. The one part is I want to say a carbon bed that tries to absorb some of the volatiles. That needs to be replaced. Obviously, when you start talking about mission to Mars or long duration stays on the moon, that becomes a problem. The other one is a catalytic burner, for lack of a better term. It basically takes the stuff in, heats it up to relatively high temperatures. I want to say maybe 500 degrees Celsius, and basically oxidizes it. And so ethylene obviously would degenerate into CO2, and CO2 and probably water. There may be some nitrogen compounds in there, depending upon the atmospheric breakup or makeup of the spacecraft. So, but I do not typically. I know for APH, they have the Advanced Plant Habitat. They have their own ethylene absorbers. I do not know if you start talking about, what should I say, plant or farm production or food production in space, if there's been adequate sizing of that, or what the impact would be on an ecosystem.
Yeah, John, I think you accurately described that the trace contaminant control system, they target certain classes of compounds, and generally compounds that are difficult to remove, and then they make some loads assessments. Right now, our trace contaminant control systems, process a small slipstream out of the general air conditioning system. And so you'd certainly have a scale-up challenge. I will say, though, we typically design the trace contaminant control system for human safety, the SMAC, the spacecraft maximum allowable levels. And so if there's lower levels that may be required for plant physiology reasons, if you're a vehicle level system right now, that's not something we're designing to. Another example would be odor. The safety level of a compound that's odorous, is much higher than the part of which it's aesthetically, displeasing to the crew members. And so we're having some challenges, with how to define that and work with that. But that would be a good thing to scale up with plants. One, in addition to ethylene, may be of interest, particularly if any of the eluted compounds from fish or plants or synthetic food, are more challenging to oxidize. And our absorber is typically trying to absorb carbon and sulfur, sulfur compounds that sometimes are deleterious to some of the catalyst used in the high temperature oxidizer.
Heather, you got another question?
I just one follow-up. That was really useful information. Yeah, I like I said, I'm not a plant physiologist, so I'm not the expert to know what all of the potential issues are. I just know that as it starts, as you mentioned, as it scales up, like yes, they solved the ethylene challenge in a small scale way, but I don't know, what the other ones were, and I just thought that would be something to consider. And the other one would be for I had asked about, can we usually it's probably the other session, but they don't like to have flames on a spacecraft. However, if you're using an anaerobic digester, to deal with, say, like the inedible biomass, that's going to be producing methane, and you're going to have to deal with that. And generally, if you could burn that off, maybe in this oxidizer, maybe you could use that as part of the fuel system, or we've been proposing to use it in an oven for cooking. But I think even like in an aerobic digester, there's going to be other volatiles coming off of it. And so those are things I think that are at a larger scale, if we're really going to do bioregenerative, are going to be issues that will have to be addressed. And that was just more of a comment, but thank you for the helpful information also.
Terry, you have a question?
Yeah, I'm not a physical science guy, but thinking long term, I would challenge the physical science people to try and approach unsupervised analysis. If you can miniaturize a GC mass spec. My example would be what was brought up when you measure the total organic carbon in the water. It's been purified and recirculated from whatever the source is. They found the total carbon was going up and up and up over months, and they had no idea. And it was the ISS, so they could grab the water and take it back and analyze it, and found out it was this methoxysilane or some kind of compound in personal hygiene stuff. And they had no idea. And it was that one chemical from whatever source was driving the water quality to the limit of 300 or whatever ppm, I forget. But, when it's going to be a long-term thing like Mars or space of months or years, unsupervised physical analysis seems to me to be the way to go. You
Yeah,
just can't predict it's ethylene all the time.
right. And that kind of gets into the third question for discussion. So what type of technologies would we need to measure and potentially even self-correct if necessary? So Gareth, you have a statement?
Oh, yeah. Well, it's kind of picking up on the volatile organic compounds that were being discussed and also the indoor air quality. So it looks like the link that James put up there looks like they're using passive samplers. I was wondering if there's any technology being developed for kind of, again, like online aerosol measurement, because you can often see volatile organic compounds turning into very small kind of like 10 to 100 nanometer particles and then back again. There's a very vibrant kind of reaction system going on there, which you wouldn't collect with a passive system. And that can affect long-term health impacts as well. So is that an area that could be explored?
I believe that one of my coworkers, Marit Meyer, actually has an experiment either that just went up or will be going up shortly to do something very similar.
Yes, I think what she's trying to do is use the passive samples, which some are getting returned as sort of the ground truth for sort of calibrating some of the more active samplers. But the goal, I think, is to move towards active measurement of particles.
Cool, because I guess the other thing is that passive samplers, if they collect a liquid aerosol, that will change the nature of its formation on the filter. So you wouldn't necessarily understand what that was when it was in the air.
Correct. And we have several types of either chemical constituent, aerosol, or particle measurements, because at least some of our ISS smoke detectors are, I'll probably get it incorrect, but optical or particle based. And so we need to be able to distinguish the morphology of the particle or aerosol to determine, is it a combustion product? Is it a, human generated dust product, or is it a regolith, dust product? And so understanding that, because if we have a fire, we don't want to we have a detection of smoke or fire, that diverts the crew from what they're doing. And you may lose science, if they have to stop in the middle of something because it's classified as urgent and we later find out it was, a false alarm. So being able to prevent false alarms is a significant area of research in the fire safety community.
Yeah, there's cross contamination that I'm aware of different types of sensors. And then on top of that, I want to say that some of the sensors that I used to work with years ago, there was also a poisoning effect whereby after the initial alarm, it would take quite a while for the sensor to clear itself, especially if there was a long tube of particles that had gotten sucked in, and it would just take forever. And so you may have this alarm going off for quite a while, and there may be nothing there by the time you get to it. So
yeah, it's very transient, the kind of whole aerosol science.
Right.
I know it's hard enough to measure on Earth when we have kind of tons of kilos of machinery we can put around that's just doing it consistently. Even then it's still noisy. So I'm wondering, is fundamental aerosol science knowledge in a low gravity environment, is that a topic area that's worth exploring with relation to kind of like long-term health impacts, and again how it relates to
well, one area I have heard discussed, I don't know how active the research area, but as additive manufacturing, both plastic and metals, becomes something we're trying to target to reduce resupply. All those generate lots of tiny particles, and those systems typically have air filtration built into them. But I know that's an area of concern, and do we have to print in a glove box? But we want to be able to print big things, so eventually we want to be able to move out of the glove box environment. And what are reasonable levels that we have to be worried about? So I would think it would be an area of interest.
Yeah, I kind of want to get over to the advanced manufacturing group now, kind of to talk about the filtration and fiber manufacturing things. So I can kind of see a thing there that crosses the T. So I might duck off in a minute if that's okay. But thanks, that's really interesting.
right? I do know that BPS, at least currently, does not have any funded research in aerosols, but like MARAD is actually funded by a different group within NASA to at least get some samples. So we did have a while back some stuff, not necessarily with what particulate type research, but we did have stuff going on with regards to spray cooling as an example. So, and I believe that C cells was looking at some type of or maybe it wasn't C cells, it was surface tension containment experiment, was looking at the stuff that was going on with regards to some of the astronauts pipetting on the spacecraft. So before we move on, I do want to at least hit the thermal aspect. Do we have any concerns about thermal, given the fact that you've got these long, depending upon where you land, you either got this severe time gradient whereby over the course of like maybe a day or two you swing from real cold to really hot at the equator, or as the one presenter showed this morning, you have this severe spatial gradient depending upon where you land at the South Pole, with regards to what you're radiating to in terms of the local environment, as well as what you're getting from the sun.
I'll just say one thing related to thermal is maybe not for the initial lunar missions, but for sustained lunar missions, food storage. Food may be acceptable to eat after several years of storage, but the micronutrients decay, and there is research by HRP and the rate at nutrients decay. But, could we use, some of the deep cold regions, around a spacecraft, or create them to provide, cold stowage for long-term, food resupply. Although typically where we'd want to put stuff is where the science would like to occur. There's talk of, could we cryogenically freeze out the carbon dioxide from a spacecraft habitat, but put our radiator in basically a permanently shadowed region, which we're probably boiling off the compounds that are of interest to ISRU and the science community. So just maybe one sort of down the road way to think about how the lunar thermal environment might be beneficial.
Bob, you got your hand raised.
Okay, good afternoon, Bob Green. Yeah, just this in the thermal management area, and I'm not an expert, but I know this has come up on one of the projects I work. Again, I work at NASA Glenn Research Center, where John works in a different group, but issues with dust on radiators, and in particular, the general thought for radiator panel for rejecting heat is use a vertically oriented radiator to avoid dust deposition. But I've heard, and don't understand the like charging staticky type environment on the moon as to whether dust would adhere to a radiator panel in a vertical orientation and thus degrade its optical properties over time and limit your heat rejection. And I suspect you could do, I bring it up because I suspect you could do a fairly simple experiment on the lunar surface, similar to kind of what other researchers have done on one or two of the Mars landers, where they were able to assess the effect of dust deposition on like a solar cell and measure the degradation over time.
I would say one other area that might be possibly BPS related would be our ecosystems and our EVA suits vent, including moisture. And I know for Mars, they're worried about how those plumes distribute, but even on the moon, could modeling or, if we could release certain contaminants, inform how widely they disperse through periodic, lunar day and lunar night cycles as they attach to dust particles and move with the dust. Because that would, I think, inform how much more filtering we would need to do, of our systems before we would go to Mars and try to meet more stringent planetary protection requirements.
So, so this would be from a planetary protection requirement, but what
But
about the
basically
possibility?
a physics and fluids transport when you have ionizing radiation and extreme thermal. I guess I've heard of dust levitating and moving across the moon through the electrostatic illumination activity, which I'm no expert. Probably misstated it even. But
No,
to me,
I believe I've heard the same thing. Like as the surface of the moon enters from either night to day or day to night, all of a sudden the things tend to pick up a charge at that demarcation and tend to
yeah,
leap off the surface.
yeah, and will that move our contamination into areas that we're trying to maintain pristine for science? If it doesn't, great. We can vent away. But if it's causing some serious challenges, I don't know. Do we have to not vent polar molecules, for example, if they're going to levitate, far distances? I don't know.
Do you think, what about the possibility of it making the stuff more hazardous for human operations or even automated operations on the moon?
Hello, hello, hello. Can you hear me?
Yes.
This is Ron. This is Ron Creel. Yes, I worked on the rovers back a few years ago, over 50 years ago. You've hit upon some very interesting problems we had with dust and trying to clean off the dust off of thermal radiators. It did not work like we had tested here on Earth, which I keep trying to tell people. Be very, very careful. And even the vertical thermal radiators, unless you provide some vibrational source, I can't see you being able to guarantee yourself that you can keep the dust off or remove it.
Now, did you try vibration on those rovers?
No, we went strictly, excuse me. We had testing that was done out there at the Manned Spacecraft Center. That's what they used to call the Johnson Space Center before it was renamed, before Apollo 15, where they tested the dust brush, the nylon bristle dust brush, and they came up with the conclusion, said, hey, they could easily clean off suits or whatever, thermal radiators, you just brush it off. That did not happen on the moon. Far from it. Astronauts, we spent far too much housekeeping time. I'm going to talk about this tomorrow at my presentation, but that's one of our lessons learned, was that housekeeping is if you're getting in that mode where you're going to try to clean off things, you're already way behind the power curve.
So was there an examination of, say, types of coatings that might?
No, there was not. There was assumption here that, hey, you could easily clean it off with that dust brush. And in my presentation tomorrow, I'm going to show you a 2-minute video of Charlie Duke and John Young trying to clean off the dust, in which they're totally frustrated with trying to clean it off of their suits, for example. Much less the radiators. We had after the mission was over, after the final mission, Apollo 17 was over, we just sat there and we said, gosh, we have gotten those guys all the way up there to the moon and made them have to do all this housekeeping, and it didn't work.
All right. Okay, I kind of want to move on real fast to at least capture some thoughts on the second question. And besides trying to support exploration type what type of meaningful science can be conducted given the unique environment of the lunar gravity, of the vacuum, temperature, radiation, and I'm sure I probably missed a few other environmental conditions. And that's again addressed more towards, I should say, well, in terms of gravity, like gravity as a continuum. I know Bonnie started to bring some stuff there in terms of the boiling aspect. But also you've got this rather pristine vacuum environment that while you can get the vacuum theoretically on station, or at least just outside of station, there is still atomic oxygen effects. Depending what type of volatiles we vent overboard, we may have that pristine temperature or pristine vacuum. Anything in terms of temperature or radiation?
Hearing crickets. I don't know if there's a good answer to your question that you've raised there. That certainly people have to also be aware that you got to be real sensitive here to the fact that away from the lunar poles, which I guess are we destined to only go to the lunar poles, or can we go to the other parts of the moon? There are interesting other things on the moon you need to explore. Along that lines, you've got 15 days of no sun. Every month, you have 15, half the month is spent with no sun, and the temperature is very, very cold. Maybe there's some things you'd like to do with that cold temperature.
Or is there something that I know? Is there something that you can do without the lack of the atmosphere? You've got a relatively stable platform for, say, a space telescope.
Yes.
But those things would have to have an advantage over just doing them on the space station.
Right. Well, the main advantage you get is on the far side of the moon. If you put a telescope there, you don't have the any of the effects that you have on the near side of the moon. You're blocked from the Earth effect, or effects of the Earth.
The rebound illumination from the Earth. And then on top of that, theoretically, you can, unlike the James Webb, you can periodically go out and maintain it. So it'd be more like a Hubble operation.
Right. But we've got enough issues trying to get crews to the near side of the moon.
Right. All right. Well, again, here, I guess I'll move on real fast. So what kind of technologies are we going to need in order to conduct this? Are we going to need, say, and I'll throw this out, are we going to need video, automation? What type of visualization to conduct these type of studies? And I don't want to say anything that's unique, but anything that might be needed that's got a little bit more oomph to it later on. A technology that we might need to develop. I know our colloids, and this gets more to the science, but on a different activity that I'm involved with, but our colloids folks are very much interested in using microscopes. Is that something that we'd want to use on the moon? Is there something that we'd want to have specialized with regards to that in terms of handling the regolith? I know that they were talking about with regards to the lunar landers being able to mine the stuff or dig up the stuff and sample the soil. How do we prospect?
one thing I wonder is just, I've heard expressed by others, is, we can pick up enough rocks and regolith in the first moonwalk that exceeds our ability to bring them home. And so what instrumentation, whether it's things we bring into the habitat, which if we do, are there common instruments or technologies that we can, share between, ECLIS, Crew Health and Performance, and the geologist, to help screen what do we want to bring back, or those sensors that can move between inside and out, or they live outside. To me, it's not clear to me, what would you use for screening on the moon? Although I've heard about, X-rays and MRIs, but, that might be useful to define somehow.
All right, should I move back to the first question if I don't hear anything?
Is it okay if I ask a question?
Go right ahead.
Hi, yes, Jonathan Breakout, Virginia Tech. I just had a question about the spatial and temporal gradients and temperature that are happening in these lunar environments. So I specialize in something called phase change thermal diodes, where the heat can conduct and spread very effectively in one direction, but in the reverse direction is highly insulating. I also do it in such a way that it's independent of gravity. So this could work in micro or reduced gravity environments. And so I guess I was just kind of throwing it out there. I'm still learning the NASA and the lunar communities here. If there were any potential interests in applying this sort of thermal diode technology to any of these lunar applications or systems.
Interesting you bring that up. We had no fewer than 5 fusible mass tanks on each rover. 2 in the rover around the batteries and the drive control electronics, and then the Lunar Communications Relay Unit had 3 phase change material fusible mass tanks. So we've been there. It was very successful, and I even used to have one of the wax boxes in my attic, but I didn't realize that the wax was going to melt away, and it did. It did.
Now that was only to last for the short duration of those Apollo missions, correct?
That's true. That's true. Although we can recycle. If you could shade it, somehow, and you will get shading. Somebody mentioned before about the levitation of dust at the sunrise, and that is a phenomenon that's been fairly well proven out. Brian O'Brien from Australia, before he passed away, he did a lot of work on that. He had a lunar dust detector, and he could determine all that went on in that phenomenology.
Did he? No, was he using? Oh, geez, sorry. Sorry about that. I don't know what I did, but give me a sec to get back. So was that experiment able to run through multiple cycles in terms of the?
Yes. Do y'all know here that we turned off all the Apollo Lunar Surface Experiment package sensors in 1977? Why did we do that? For budgetary reasons. We have not gotten any data from those systems for all these years that we could have had, but it's one unfortunate thing we don't have.
Is that something that they could is there a way to turn it back on?
That question's been asked. I don't know the answer. Certainly you had the radioisotope thermoelectric generator that provided the power for those. I'd have to look at the half-life, but that's diminished a whole lot here. It's been how many years? That's 1977. That's over 40 years. So that was their power source for the. And by the way, I think y'all should factor in the JPL folks here for their rovers, what they've learned about dust and how to handle that. Granted, it's an atmosphere. It has an atmosphere. It's not atmosphere less like we got on the moon, but they did learn an awful lot. They did have wind that cleared off the radiators. Now they've gone totally away from radiators into a big RTG system on the Curiosity and the other one, Perseverance.
Well, they still need to reject the heat, don't they?
Yes, that's true. Yes. And the Russians lasted for 11 months using a isotope heater system on the back end, where they would once they closed it up, they could survive for 11 months.
So that was basically because Mars runs at about 100 degrees below zero in terms of Celsius, or
yes. But they were presented with a problem on Curiosity, that an opportunity that dust blew onto the radiators, solar panels and the radiators, and it created high temperatures, much too hot. And they got lucky that one of them, the wind came along and blew the dust off. We can't bank. We don't have wind on the moon.
all right.
Y'all have a lot of good issues. I don't know the answers to a lot of them, but I will give some answers to dust control tomorrow, and it has to do with isolation technologies. Keep the dust outside.
Do you know if they've looked at? I know the what is it? The microchip industry has very tight requirements in terms of cleanliness. Have they looked at any of those techniques, or is that a problem in terms of? I think in their case, I know they tend to have a high use of consumables in terms of like water and highly pure water, as well as something, I think, what do they call it? A piranha wash, which uses some really I want to say nasty chemicals.
Yep.
So, all right. Let's move back to the first question, if I can work this. Okay, so in terms of living, manufacturing, and doing anything else on the moon, we focused in on the dust in terms of the thermal impact. We've talked a little bit about measuring volatile compounds in terms of or quantifying volatile compounds in terms of the living space, as well as what happens to it if we decide to use that vent. Anything else? I know that some of the pictures that they were showing for the regolith, they were talking about having, I want to say, I will call it blast shields, but plume dissipators for the landing pads. Are they going to need something similar or not?
Yeah, just one thing that does get talked about a little bit in life support is, using spray processes. And, although, dimensionless parameters of fluid flow and stuff should guide us, is there anything, do we need to validate, those correlations in a 1,6G environment? Might be of interest for either like air stripping of compounds, out of water, or certain times we want to spray to, like, say, if we could nebulize an absorbing liquid, then we could absorb CO2 out and we get tremendous surface area. But we always have challenges with, mist control and microgravity. And so in theory, it should be easier on the moon, but things like that could be of interest, unless people who know may say, oh, that's no research required. I don't know.
Well, I guess the one,
I think you're right about the latter comment. For us, they did test aerosols and liquid sprays, but any pressurized system that you bring to the moon has the danger that it's going to damage the suits. And the people in Houston, they don't want that at all.
so that would, so that's in terms of the EVA suits, but like internal to the spacecraft or
Perhaps,
the tools.
perhaps.
I know that one of the things that keeps popping up from time to time is just with regards to aerosols is like this whole thing with COVID. So do we really understand how aerosols form and how they spread? Is there a do the little aerosol particles coalesce into larger droplets or vice versa? Do they undergo some sort of instability and split apart into finer particles?
This is Terry again. That has been well studied. And yes, small particles agglomerate in large ones, but they don't typically separate after that. But there's a lot known, but not necessarily in microgravity or 1/6.
Now, if you start looking at a volatile compound, and you've got it in 1/6, let's take like ethanol, the vodka type stuff. You have a mist of that. It's going to take a lot longer to say fall, and thus you may have more time for it to evaporate as it's falling in a lunar gravity environment.
Right.
So. All right.
And just one area, again, this probably falls into the planetary protection realm, but I guess how does our biological waste that we want to dispose of outside, the Apollo fecal bags, for example, were disposed of on the surface, I guess, and urine bags too. Do those organisms remain viable, or is the lunar environment sufficient to, deactivate them? We're going to be inventing compounds with microbes, so some small scale experiments early to understand that would be helpful. I've heard there's some interest in returning to an Apollo site for many reasons, but one would be to see if the biological waste we disposed of 50 plus years ago was still viable.
You have to realize all those packages have been through over 600 cycles of plus 250 plus 260 down to minus 280, 600 times.
So depending upon and that may lead to other questions just in terms of how do you expose it? Do you use the old scout method whereby when you're done taking care of your business, you basically bury it in the soil and you put a stick up saying, don't tread here?
That's a good idea.
That's a whole nother fascinating field where, the enzymes they use for the PCR analysis for COVID and everything else, it comes from bacteria, enzymes in bacteria that can live at over, almost in boiling water, in hot springs. So it would be interesting to see if all those cycles caused evolution and certain bacteria could survive all those cycles. It's a good question.
No, or did it? maybe evolution, or did they go into some sort of stasis, whereby if they were brought back inside?
And long term, if anybody went to the Mars dust conference in Houston 3 or 4 years ago, all that came up, and it was pretty interesting for me, for an air pollution guy, that it seemed like half the people were more worried about Earthlings contaminating Mars microbiome versus the other way around, bringing Mars bugs back to Earth and contaminating us. It was about 50-50 for planetary protection either way.
All right. Well, we're going to restart this session so everyone can have a little bit of a break to either refill their water bottles or hit the restroom, whatever. But in case you don't come back to this session, let's see. I'm supposed to remind you, oh, wrong way. That tomorrow's session starts at 10 o'clock a.m. Eastern Daylight Time, and that Harrison Schmidt will be one of the first people to speak at the beginning. As a reference, Harrison was one of the last men on the moon. I'm not sure if he was the geologist or not, but he's the conference organizer.
Yes, he was. He was the geologist.
The conference organizers were really excited to get him to speak tomorrow. So this may be well worth the wait. So, all right. And we'll see you. For those that want to come back, we'll see you in about 10 minutes and talk some more. Or
Can you give us a hint what the next hour would be about?
More of the same.